All right, let's get started then. So today we're going to talk a little bit more about these binary search trees and balanced binary search trees and all the fun things we can do with it. Before we start on this topic, I wanted to remind you again about the programming contests. There will be a special practice contest that ICPC will organize. This is on the Saturday right before the big competition. This is on February 28th. And it will happen between 2 p.m. and 5 p.m. And of course, the actual contest is the following week on March 6th. And that goes on from 2 p.m. to 7 p.m. And there'll be some kind of an opening ceremony prior to the 2 p.m. And there'll be some award ceremony after 7 p.m. So make sure that you leave yourself time for all this fun stuff. Okay. Now there are also some announcements for the contest. So I need to share with you that there are going to be some new rules for this year's competition, just because everything is special this year. The first thing is that even though you'll be competing as teams, remember each team has 3 members. However, each of you will be in your own home or wherever you'll be on your own computer. You'll be at whatever location you're at. And you'll be communicating with each other most likely via Discord, although that has not been figured out yet. When the competition starts, what you will do is to divvy up the problems between yourself, and whatever problem anyone solves, the whole team gets credit for it. And of course, you can always talk to each other through these communication channels that would be set up. Now, I have no idea how they're going to monitor all of this, but apparently they're working all of this out. This is why it's really, really worthwhile to attend the practice session on February 28th. So that you get a sense of what it is that you're going to expect the following week. The other final important thing is that until the previous competition, there were 2 divisions, Division 1 and Division 2. Division 2 was for schools that were where the players were all beginners. Typically, we have competed in Division 2. Well, actually, in the past, we used to compete in Division 1, and then when more recently, we've been competing in Division 2. However, this year, there's going to be only 1 division, which means everyone is competing in the same group. There will be more problems that will be given to you. I think you'll be given 11 or 12 problems, or maybe even more. And so you will have a whole bunch of easy problems as well to work with. So that's these are the things that you guys will need to know. They've announced it, and I guess are there any questions about this?
How long is the competition?
There you go. 2 p.m. to 5 p.m. So it's almost always 5 hours. Once you get started, it's just way too intense, and the 5 hours just go by. Other questions?
Yeah, and then once you get the Discord link for the server,
yeah,
you be sending to us. Does ICPC have their own server on Discord, or will we do it ourselves?
What was that, Lazaro?
Hello? Hello?
Did we lose you?
I hear Lazaro speaking. Well,
Hello?
Yeah.
Okay. Yeah. Yeah. I was asking the Discord server, does ICPC have their own?
Uh-huh.
And
ICPC.
yeah, do they have their own server on Discord?
They're going to provide us with that information. They haven't quite figured all that out.
Okay, perfect. Thank you.
Yeah. Any other questions? Also, I guess many of you probably don't know your teams, right? Do you see this?
We see your slide.
You see my slide, not the Excel spreadsheet.
No, not that.
Okay. All right. Let me then. Oh yeah. Okay. You see this now?
Yes, now.
Yeah. It's probably a little small, but if you can read this, there are 4 teams. There's FIU Panthers, there's FIU Gold. Whoa, why do I have FIU Panthers twice? Somewhere I must have gotten the name mixed up. So one of them is Panthers, one of them is Gold, the other is Blue, and the other is Rory. And these are your team members. Do you see them?
Yes.
So make sure you find your name, and I will also send you email to confirm this. And one of the things I strongly recommend for you is once you find out who your team members are, make sure they show up for the competition. Okay? Get in touch with them through your channels, through your Discord channels, and keep sending them messages, make sure they don't forget and they show up for the competition. Clear?
Okay, perfect.
Okay. All right, so let's go back to what we were doing. Okay. Are we back to the slides for you?
Yeah.
Okay. All right, so let's talk about binary search trees. So this is what we talked about last time. We talked about binary search trees where for every node, the values on the left side, the left subtree are all smaller than the value stored in the node. And all the items in the right subtree are values that are larger than the value stored in the node. And this property is satisfied at every node in the tree. We went one step further and we talked about something called red-black trees. These red-black trees are essentially binary search trees with some additional properties. And the additional properties are shown here on the right side. The root node, so every node has a color. The root node is black in color. The leaves are all colored black. Then there are a bunch of red nodes. There may be some red nodes in the tree, but the red nodes are never adjacent to each other. And what the most important property is that when you take any path from the root to a leaf node, the number of black nodes that you encounter along that path is always the same. So that means that all the leaves are at the same, what's called as the black height of the tree. So the number of black nodes that you encounter from the root to any leaf is exactly the same. In this example, regardless of which path you take from the root to a leaf, you'll encounter 3 plus 1, 4 black nodes along the way. And you can verify this for all the nodes in the tree. Okay. And as long as you maintain this property, it turns out that the height of the tree is never more than 2 log n, which means that the height of the tree is big O of log n, which also means that the basic operations of insert, and delete, all three essentially become proportional to the height of the tree, which in this case is at most 2 log n. So therefore, all three operations become log n time operations, and therefore all three operations are extremely efficient. And last time we kind of quickly went over how to do search, insert, and delete. Well, we didn't quite complete everything there. The search is really easy. It's exactly the way you do binary search. The insert is in a binary search tree, in a simple binary search tree is quite easy. You essentially do a search, and wherever you fail in the search, that's where you insert it. And it turns out that for the red-black trees, you do exactly this, but then you do some additional operations where you may have to fix the tree that you end up with, and make sure that it satisfies all the properties of a red-black tree. I haven't shown you that code here. We won't have time to discuss that. But as I said before, the best thing to do for you is to take the code from wherever it's available, and then to simply use it in your programs, and make sure that you're able to use it effectively. And it's important to note and important to understand that these red-black trees are always going to be more efficient than your regular binary search trees. In particular, they will take care of all these or what are called as worst case scenarios, where you end up with trees that are extremely imbalanced. We didn't really go through the delete procedure. It's a little more complicated than the insert. And again, I am not going to go through the details. If you guys are interested, we can do this after the competition. For now, I want to move forward with the assumption that we know how to use these functions in our programs and make them more efficient. And so we're going to stop with that and try to move forward. What I want to tell you is that there are Java implementations of red-black trees. In fact, they're called the tree map class and the tree set class. Both of these are essentially implementations of red-black trees. So if you go and search for tree map and tree set, you will be able to figure out exactly how these classes are defined, and you'll be able to figure out all the operations that are provided in these classes. And there are some very nice examples on the web for how to use them. I've provided you with some links for each of these. So that's with the examples in Java. For those of you who are Python fans, that also is possible. A Python implementation is provided. And I did download this code, and I tried it, and it works quite easily. It's pretty well-written code. You're definitely welcome to use that. There are some other people who have implemented this as well. So it is important to understand that in Python, it's not part of some standard library. You have to you can take these codes and use them in your programs. They will work just fine. Any questions about this? Could I have some of you show your video so that I know you're there?
Okay.
Thank you. Appreciate that. So, any questions about this? Was all this reasonable for you?
Yes. Yeah.
Okay. Okay. All right. Great. One of the things that I wanted to focus on for these red-black trees is an important operation called the rotation operation. And this is a key concept that you need to understand. This rotation operation is what makes binary search trees, is what allows us to convert regular binary search trees to balanced binary search trees, in particular the red-black trees. And way we are going to do this is to actually visit a website. So give me a minute or so to get this going. Okay, let's go to All right. Do you see the browser or do you see the slides?
We see the slides.
You still see the slides. Okay, I have
Yeah.
to fix that then. Okay. All right. Okay. You see the browser now?
Yep.
Yes.
Yeah.
Okay. So what you see here is the important stuff. Given any binary search tree, you can look at any node in the tree, and you can perform what's called as either a rotate right or a rotate left operation, and these operations will look the way it's shown here. So you see here that if you rotate right at Q, it will send P as to be the root, and Q will become its child. So the rotate operation simply makes the parent the child. Okay, so instead of P being a child of Q, you'll have Q being a child of P. But as you do this, you have to fix the subtrees. So Q used to have C as its right subtree, that's still true. P used to have A as the left subtree, and that is still true. But now B, which used to be the right child of P, now gets attached to Q. And you see that in the picture over here on the right side. Do you see this animation that's shown where when you rotate at B, A goes up and becomes the parent. And the second subtree now, instead of hanging off of A, becomes a subtree of B. So this operation is called a rotate operation. Did everyone understand this? Now, what is important to understand is that whenever you rotate, it still keeps the tree to be a binary search tree. Now, why is that? Well, let's look at this structure on the right side. Everything in this subtree called alpha must be smaller than the value stored in A, because it's in the left subtree. Everything stored in gamma must be larger than B, because it's on the right subtree, it's on the right side of B. And what about the things in beta? Well, in order to understand this, you need to understand that the value in A must be smaller than the value in B, because A is was the left child of B, or B was the right child of A. Either way, B seems to be larger than A. All the things in this subtree beta are between the values A and B. Okay. So therefore, either they are the right subtree of A or they're the left subtree of B, depending on which one is the parent. So so even though I did the rotation, everything, all the binary search tree properties are still satisfied. The only thing it changed was that it may have changed the height of the tree. Okay. Other than that, it keeps the values in the right order. In fact, it's also shown over here. It says that A is always smaller than P, is always smaller than B, is always smaller than Q, and it's always smaller than C. And the same is true over here. It still keeps that ordering satisfied in exactly the same way. And all that is satisfied even here, where it's not just one node, it's an entire subtree that hangs off of A or B or C. Okay. So these rotations are extremely important because they allow you to rebalance the tree if one side becomes too big. So if the height of the tree is too big on one side, you rotate it so that things get more balanced. And what we know now is that balancing keeps the binary search tree properties all satisfied, and it doesn't hurt the ordering in any way, shape, or form. So in the red-black trees, what they do is that they will occasionally go and perform some rotations so that the tree becomes reasonably balanced. And it prevents things they occasionally allow for rotations. In a standard binary search tree, we don't perform any rotations, and so therefore the tree can become heavily imbalanced. What we know is that even if you have a skinny long tree that's all on one side, that also is a binary search tree, except that it's very imbalanced. That would never happen in a red-black tree because of all the properties that we imposed that it satisfy at all times. And that's why red-black trees are much more efficient than standard binary search trees. And that's all I have to say about rotations. Are there any questions before we go back to the slides? Okay, no questions. Good. So let me go back to. All right, we're back to the slides, I hope.
Yes. Yes, we can see
Okay.
the slides.
Okay, good. All right. So this is what I said earlier. The rotations preserve the property of being a binary search tree. All your orderings are still satisfied. Everything in the left subtree is smaller. Everything in the right subtree is larger. Even though you went and rotated it, the rotations were done carefully enough that this property remains to be true. Okay. So in general, we can start from any binary search tree and rotate at any node you want, and the binary search tree property would remain satisfied. And the good thing about this is that if your tree is very imbalanced, by doing some rotations, we could bring back some balance to the tree. Okay. So that's what we say. Of course, the process may change the height, which is, of course, what we typically want. Okay. So let's start with the first problem that we want to solve using these red-black trees. We want to know, how can we sort using red-black trees? And I would like to hear some suggestions from people here. How would I go about doing this? Let's say you're given some red-black tree code. You can use any of the operations you want on a red-black tree. The question is, and I give you a set of items. So let's say I have an input of n unsorted items, and you're allowed a tree. You can do whatever operations you want. Remember, the three standard operations on a tree are search, insert, and delete. Using that, how do I sort this list of n items?
Well, I read a little bit about red black trees, so I know
Yeah.
they're like binary trees.
They're binary search trees, of course. I told you that already. Yeah.
Okay. But maybe I didn't understand the question. Can you please repeat it one last time, please?
My goal is to sort this list. Okay. I have n items. They're unsorted. I want to sort them. And I am given as a data structure a red black tree. You can use it as you please. Do whatever you want with it. And what that means is you have the three basic operations of the red black tree. You can either insert into it, delete from it, or search for something. And think of these n items given to you in an array, let's say. Okay. Now the question is, how do I do this sorting? With the help of a red black tree. I don't want to use anything else.
Okay, okay.
Is the red black tree of any use in sorting? Remember, it's a binary search tree, so it has these nice properties. Things on the left side are smaller, things on the right side are larger, etc., etc.
Yeah, definitely. If we start inserting these items in the red black tree, it will.
Okay. Well, it will give me a tree. How does that help me to sort?
Well, you know, like the leftmost element in the node in the binary tree,
Yeah.
the red black tree is
Yeah.
going to be the smallest value.
Okay.
I mean, so then wouldn't you be able to just go from like the bottom up on the left side and then?
Good. Yeah.
Yeah.
Okay. Yeah, you have definitely that's a good start, but it doesn't quite solve the problem.
No.
Anyone else? How can I take a red black tree or a binary search tree with all the items already inserted into it and produce a sorted list from it?
So can you just go like recursively look at the left subtree?
Yeah.
And then after that print the root value, and then
Yeah.
after that print the right do the right subtree.
Very good. So what is that ordering called?
In order.
That's called in order traversal. So we need to do something called an in order traversal of the tree. And this is something I'm sure that you've seen somewhere in your programming 2 class. So it's going to come back to haunt you now. So let's go over this quickly. So here is our algorithm. We start with an empty red black tree. And we take each of the items one by one and apply the insert operation. And at the end of inserting it, you would have a red black tree with all the items. Of course, you know already that inserting n items into the tree can be done in n log n time because each operation is log n, right?
Right.
And then once you've done this, you perform an in-order traversal of the red black tree and simply print it out. Now, what's an in-order traversal? In-order traversal always goes to the left subtree first, then prints the root, then prints the right subtree. And that's exactly the order you want because you know that all the items in the left subtree are smaller, all the items in the right subtree are larger. And that property is satisfied at every node in the tree. So for every node, you would visit the left child first, then the node, then the right child. So a simple in-order traversal will take care of this. And if you don't know how to do the in-order traversal, I know some of you are already searching, so you can figure this out. It's a 3-line recursive program,
Yeah.
very simple, and you should be able to write this up. So what this means is I can do sorting using any of the sorting procedures, but I can also sort using red-black trees. Okay, is that clear? And what's nice is that it does this in n log n time, which is exactly what we can do with any of the best sorting procedures, right? So this is very efficient. It's just an extra feature of red-black trees. This is not what you would typically want to use it for, but we know we can use this. And this is something that it's useful to understand what you get out of a red-black tree at any given time. By the way, you could have done this even with a regular binary search tree. What's the difference?
There shouldn't be any difference, no?
The algorithm is not different, but the time complexity is different. And why is that? Because the n items inserting may not happen in n log n time. It could take n times h, which is the height of that tree, which could be large. If the height is big O of n, then it could become an n squared time operation. That's all it says. Okay. So if you randomize your items before inserting into a binary search tree, you'll probably get a pretty good tree. So you don't need the fancy stuff of red-black trees. You could use a regular binary search tree, but make sure you randomize the order before inserting it. If you insert it in sorted order into a binary search tree, what happens?
We will get like a diagonal.
Yeah, if you have a regular binary search tree and if you keep inserting larger and larger items, it'll all slant to one side and you'll get one long skinny tree. And how long, what will be the height of this tree? Essentially its height is going to be big O of n, right? So then all your insert and delete and search operations become very expensive and you get big O of n as the height of the tree. That's what you're trying to avoid. So if you just jumble it up, randomize the order, and then build the binary search tree, you'll get a pretty reasonably well-balanced tree in the end, and all will be fine. Or you could go and use a red-black tree so that you will never have a problem. Okay, especially if you're going to do inserts as well as deletes, then you're better off using a red-black tree. If you're only going to do inserts, all you have to do is to randomize it, jumble up the order, and then build the tree. Is that clear? Everyone okay with that?
Yes.
Okay, so one important thing we learned from this slide is that if we are given any binary search tree, doing an in-order traversal will give us the sorted order. That's one thing you need to take away from this. And if I wake you up in your sleep and I ask you, you should be able to tell me that. Yeah? Cool?
Yeah.
Okay. Of course, red-black trees are only a special type of binary search trees. So therefore, an in-order traversal will give you the sorted order. All right. Next. So far, what we have achieved is to perform 3 basic operations on a binary search tree, which is search, insert, and delete. Next, we are going to add 2 more operations to this list and figure out how to do them efficiently. The 2 operations are called rank and select. So let me explain what these operations are. The rank operation will tell you the rank of an item in a set. Now, what does that mean? It means it's the index of this item if you sort the item and place it in an array. So if my set S has all the numbers from, say, 1 through 10, then the number 7, once you sort it and put it in an array, will sit in the 7th location. So its index is 7. Sorry, its rank is 7. Is that clear? So the rank is basically its index once you sort it out. If you have only even numbers between 1 and 10, then the number 6 will be in the third location because it's the third even number. So its rank is 3 in the set. So rank is simply where it sits in the sorted order. Okay. So if I were to rank all your GPAs in descending order, your rank will tell me where you stand in class, right? So it's the same thing over here. If you rank all the values, if you put them in sorted order, you want to know where each of these items stand. Okay. Now that's the first operation. There is also a second operation called select, which is exactly the opposite. In the select operation, I'll give you a rank and I'll say, find me the item with rank 6. So in select, I give you the rank and I ask you what the item is. In rank, I give you the item and I ask you what its rank is. Is that clear?
Yes.
Okay. So these two are very closely related operations. Now the question is, how do I do it in any data structure? What you'll find is that again, using arrays or linked lists, both these operations are not very convenient because if I'm going to constantly insert and delete items, the rank will keep changing and I have to keep track of this. And so I'd have to update the rank of everything in order to be able to answer these queries efficiently. So let's then focus on the binary search trees. In particular, we'll focus on the balanced binary search trees, the red-black trees, and ask the same question: how are we going to compute the rank of any item in the tree? Or also, how are we going to select an item with a given rank? Is everyone clear about the rank and select operations before I move forward?
Yes, Professor.
Yeah? Okay. All right, so that's basically our problem. And remember, we are assuming that we are allowed to insert and delete items at any time. So the rank operation of X may give us different answers at different times based on what other things got inserted and deleted. So I may keep asking the same question, but I may get different answers at different times. Is that clear? Okay, so that's part of the challenge. Our challenge is at any given time, I'll ask you either a rank question or a select question, and you have to give me this answer as efficiently as possible. Now, the only way we know this is to keep a sorted list and to keep track of the rank of every item and keep this updated every time I do inserts and deletes and figure out the answer. So what this means is that these operations essentially are, this is our standard list. What we know is that the rank and select operation is, we only know how to do this in order n time. Because if I insert something at the start of the list, then the rank of everything else changes. If I delete something from the start of the list, the rank of everything changes. So every time I make these operations, I have to go and update the ranks of everything. So maintaining the rank becomes a serious challenge, right? If I have to maintain this at all times all through the inserts and delete operations, this becomes too expensive. I cannot quite maintain this and still perform the other operations efficiently. In particular, I cannot perform rank and select operations efficiently because it's constantly changing. All right. What we're going to figure out next is how we can do this efficiently. Okay. All right. Any questions so far? Okay. So these are, by the way, the red-black trees we've talked about so far are what are called as dynamic red-black trees. They're not static in the sense that you're constantly inserting and deleting things from it. And so therefore, they're always going to be called dynamic data structures because of operations like inserts and deletes. So we should skip this slide. I don't know why I have it here. We already talked about this. So I'm going to tell you how we can do rank operation first, and then you'll see that we can also do select operation quite quickly. The way we're going to do the rank operation is by adding some extra information to each node in the red-black tree. Now, what is important is that whatever information I store, I should be able to update it efficiently. What we figured out earlier is that if I store the rank of that node at every node in the tree, I'm in trouble because every time I insert, a whole bunch of ranks would change. So it would be silly of me to try and store the rank value in each node. So I'm going to say, forget it. I'm not going to store the rank. Instead, I'm going to store some other information which will help me to perform this operation efficiently. And does anyone know what I'm going to store at each node?
Would it be the number of elements in the left subtree and right subtree?
Something close, yeah. So what we're going to store is something called the size information. We're simply going to store the size of the subtree at each node. And it turns out that using this, I can figure out the rank very, very efficiently. And let me show you an example first instead of showing you the code first. So I don't have an example. Let me see. Give me a second, please. Where's my red-black tree example? Here you go. Yeah, all right. So if you look at this tree, I am going to store at each node an extra piece of information called the size. So in particular, over here, I'm going to, because it's a leaf of the tree, the size of its subtree is just of size 1. So all the leaf nodes, this guy, this guy, this guy, this one, and this one, all of these will have an extra piece of information which would be 1 stored in it. As you go up the tree, the size information will change. So for instance, over here, what would be the size I will store? I will store the size of the entire subtree, which is basically the entire tree. And we know that there are 4 on the left side, and what is it, 8 on the right side, 12 plus 1. So there are 13 items in this tree, it seems. So I would store 13 over here at the root of the tree. Okay. What would I store here?
2.
You would be storing 4 because this subtree here is of size 4.
Oh, okay, yeah.
Right?
I see.
What
Yeah.
would I store here? What would be the value stored in 85?
Is it 10? No. Let me count.
Go ahead and count.
8, sorry.
So it's going to be 8, right?
Yeah.
So this guy here will be
2.
2. So 2, here it's 1, 1, 1. Then here it'll be 3. Here it'll be 4. So, so you know exactly the height of each node in the tree. Let's say we do a lot of work and figure this out. Now, the question is, if I had this size information, how will that help me to figure out the rank of, let's say, this node here at the top of the tree? Well, it's very simple. The rank of this guy is, well, Ricky already said this. Ricky, you want to tell us how you figure out the rank of this node?
It'll be the left subtree and then +1.
+1. So you know that all the things in the left subtree are smaller than this item. They're all going to be, if you sort this list, they're all going to be before this number 61. And then you have to count the index of 61. So it's going to be 4 + 1, 5. So the index of 61 is just 5. It's simply the size of this left subtree +1. Is that clear? So the good thing about these red-black trees is that we know left subtree has all things that are smaller, and you know exactly how many items there are if you store the size of that subtree. So I don't have to go and count anything. I'm just going to store that information at that node. So I can figure out the rank of the root quite easily. If I want to figure out the rank of some other node, it turns out that it's still not that difficult. And that's what we're going to look at next. Any questions about this so far?
Wait, yes, I do. How come 16 and 65 are red?
Because this is a red-black tree.
But aren't our leaves supposed to be black?
Well, this is a artifact of how the thing is implemented. 16 actually has 2 children.
Oh.
And those 2 are null nodes, and they are black in color.
Oh, okay. So we're counting those.
It's a small artifact of how it gets implemented.
Okay. All right. Thank you.
Okay. Yeah. All right. So back to our problem of figuring out the rank. Okay, here you go. So here is pseudocode for how you compute the rank. And as you can see, it's basically a 5-line code, 5-line function. How does this work? Remember, we want to find the rank of X in a set. That's what we really want to do. What we're going to do instead is to modify the function so that we find the rank of X in the subtree rooted at a node. Of course, if that node is the root of the tree, it's equivalent to saying, what is the rank of this guy in the whole set, right? Now, here is how this code goes. For each guy, each time in this, well, the first thing in the function is to figure out the size of the left subtree +1. That gives you the rank of the root of the tree. Okay, so R now is the rank of the root of the tree. So this is your computation for the rank of the root of the tree. Then we're saying if X is equal to Y, then what you're looking for is the rank of the root of the tree. So all you have to do is to print out R. Otherwise, you're going to check if the value you're looking for is smaller than the value stored in the root. In that case, you have to figure out its rank in the left subtree. Otherwise, you figure out its rank in the right subtree, but then you have to add R to it. Remember, when you go down to the right subtree, you will only figure out its rank within the right subtree, but then there were a whole bunch of items that were prior to it. And so you add R, those are the number of items in the that are prior to whatever comes in the right subtree. So either the value is going to be the rank in the left subtree of X, the rank of X in the left subtree, or the rank of X in the right subtree plus this number R. Remember, R is the rank of the root of the tree. So what we've done here is to write a recursive procedure for figuring out the rank of any node given the size of every node in the tree. So here we are assuming that every node has stored in it the size information. We haven't said how it's done, but for now, let's just assume it's there. We are now figuring out how to do rank very, very efficiently. Now, why is this efficient? The reason it's efficient is because you're traversing from the root of the tree all the way to where the node is. So it's no different from search. It's in every step you go down the tree. So the time complexity is big O of log n, because if we do this on a red-black tree, we can be sure that the height is going to be big O of log n. Is that clear? So what we've done is something magical. Once we have a red-black tree, if we can store extra information about the size of every node in the tree, I can now figure out rank of any node in the tree. Now, this is something special because this was not possible before. Now, you can insert and delete things as you wish, and you can still go and quickly figure out the rank of any node. And it still takes you only log n time. Clement does not look happy. Ask me some questions.
Oh no, I was just like, no, I was just like taking notes on what you said, what you were saying.
Okay, but I want you to follow with me. I want you to keep up pace with me. So tell me what it is that didn't quite gel for you. Don't be shy.
I guess I'm like, I mean, I'm just looking at like the code itself, and I'm just like trying to like see, like visualize it, like.
Okay.
Yeah.
So what you're asking is, somewhere here in this tree is X. I don't know where it is. Okay, but Y is the root of the tree, and I want you to figure out the rank of this X in this tree. That's what you're asked for.
Yeah.
Okay. So instead of giving you the set, I'm simply giving you the pointer to the root of the tree. Now, I don't know where X is. It could be right at the root, or it could be in the left subtree, or it could be in the right subtree. I don't know this.
Yeah.
Now, we're saying, let's first figure out the root, the rank of the root. Once we have that, all I have to know is the value you're looking for smaller than the root or larger than the root? If it's smaller than the root, its rank is going to be smaller than the rank of the root, right?
Right.
If it is equal to the root, that's the easiest case. It's simply the rank of the root. And we know exactly how to do this. It's simply that first statement, which is the size of the left subtree plus 1. If it is smaller than the root, well, we recursively go and search in the left subtree and say, okay, forget about the rest of the tree. I'll just solve the rank problem in the left subtree. And life is easier because it's a smaller subtree you're looking at. If it is larger than the root, well, it's still the same. It's still easy. I still have to figure out the rank in the right subtree, but I have to add some extra to it. Because remember now, its rank is going to be larger than the root. And when we do the search in the right subtree, we'll figure out by how much it's larger than the root.
Okay, I think
that part is not so clear, is it?
Yeah.
Okay.
There we go.
All right.
Yeah.
Assume that the rank of the root is 5. Let's say you're looking for an item that's equal to the value stored in the root.
Yeah.
So therefore, its rank must be 5 because it's the root.
Yeah.
Done. Now, let's say we're looking for something that's smaller than the root. So we know it's not 5, but we also know something more. We know that it's smaller than 5. And it's exactly the same as its rank in the left subtree. Because it's not there in the right subtree. There's no point looking over there. It's not the root. So therefore, whatever its rank is in the left subtree, that's its rank.
Mm-hmm.
Let's go back to the example here.
Okay.
Remember this example. Let's say I want to figure out the rank of 55. Okay.
Okay.
What I do is first I figure out the rank of 61, which is the root of the tree. And that's easy because on the left subtree, I have 4 nodes. So therefore the rank of the root is 5.
Mm-hmm.
That's clear?
That's clear. Yeah.
Okay. So 55 is smaller than 61. So I say, okay, forget the root. Let's go search in the left subtree. And whatever is its rank in this left subtree here, that's going to be its rank.
Mm-hmm.
So we are now here at 52, and we're asking if y is 52 and x is 55, which is what we're looking for, what is the rank of 55 in this subtree? Now, in order to do that, well, what I'm going to do is I'm going to figure out the rank of 52 now. What's the rank of 52? I look at the size of the left subtree, which is
2. Wait,
2.
no.
2, that's correct.
Okay.
Yeah, don't add all these black thingies here. They're confusing,
Yeah,
I know.
almost.
I know. There are only 2 values in the left subtree. So this guy's rank is 3.
Mm-hmm.
We know that 55 is larger than 52. So therefore, its rank must be greater than 3.
Mm-hmm.
Right?
Right.
Now, the question is, what is its real rank? Well, its rank is whatever is the rank of 55 in the right subtree plus the 3 that are smaller than it.
Yeah. Okay.
Did that make sense?
Yeah, that made sense. Yep.
Okay. And in the right subtree here, the rank, there's only one item, so its rank is 1. It's very easy.
Yeah.
Right?
Yeah.
In fact, its left subtree is empty, so therefore this guy's rank must be 1. So in this subtree, its rank is 1, but in this subtree, its rank must be whatever is the rank of the root plus 1. So what's the rank of this guy? It's 3. 3 plus 1 gives you 4. That's the rank of 55. Did that make sense?
Yeah, that made sense.
Okay, shall we try something more complicated? Shall we try, what shall we try? Shall we try 93? No, let's try 90.
Okay.
How do we figure out the rank of 90?
Well.
All right. So let me go through the steps, and you can help me along the way. So
right.
First of all, I figure out the rank of the root, which in this case is 5.
Mm-hmm.
Right? Why is it 5? Because there are 4 in the left subtree plus 1.
Mm-hmm.
So I know very quickly that the rank of the root is 5. And I know that 90, which is what I'm looking for, is larger than 61. So it must be more than 5. So how much is the rank? Well, I'm going to start the search in the right subtree, which is everything rooted at 85.
Mm-hmm.
I will figure out the rank of 90 in that subtree rooted at 85, and I will add to it everything that I skipped earlier, which is 5. Did you understand that?
Yes.
Okay. So now I can completely ignore the root. I can ignore the left subtree and simply focus on the right subtree, figure out the rank of 90 in that smaller subtree, and add to it 5.
Mm-hmm.
Is that clear?
Yeah, that's clear.
So for instance, the smallest guy here is 65, right? In this entire subtree, it's 65. What is the rank of 65? It's everything that you skipped, which is 5 of them plus 1.
Yeah, so 6, yep.
So it's 6. So what's the rank of 90? Well, it's the same thing. You find its rank in the subtree and then add to it the 5.
Okay. Yeah,
okay. So in order to do that, I'm still going to go right, which means I have to add to it the rank of 85 in this subtree, which is how much? Since there were 4 in this subtree, the rank of this guy is again 5.
Mhm.
I skipped 5 over here. I'm going to skip 5 more over here. So I've skipped a total of 10 so far.
Right.
Okay. So now I'm going to focus on this subtree and figure out the rank of 90 in there and add to it the 10 that I skipped over.
Mm-hmm.
Clear?
Clear.
So what is the rank of 90 in this? Well,
One.
it's 1 because it's the smallest guy there.
Yeah.
So its rank is 11 because I skipped over 10.
Okay. Yeah, it clicked now. I got. Yeah.
Is that clear?
Yeah.
Everyone okay with this?
Yeah, actually, the example also actually helped.
Yeah, yeah,
That helped a lot. Yeah.
yeah. All right. So now let's do the other operation, the select operation. Now I ask you, find me the 11th item in the sorted order in this tree. You know the answer already because we just did it. We just said 90 has rank 11, right?
Mm.
So how can we arrive at 11? So I want to figure out the 11th smallest item in this tree. Here's how I'm going to do it. I start at the root. I figure out its rank, which is how much?
5.
5. I know 90 is larger than the root. So I'm going to skip the entire left subtree and the root. I've skipped over 5 items. I keep track of that. And I find the, so now instead of looking for the 11th item, since I skipped over 5, I'm going to find the 6th smallest item in the right subtree. Is that clear? 11 minus 5 is 6, right?
Clear. Yep.
So I find the 6th smallest item in this subtree, rooted at 85. Now, what is the rank of 85 in this subtree?
10.
No, rank of
5.
85 in that subtree is 5 because there were 4 in its left subtree and 1 for it. So I know that 90 is bigger than 85, so I have to subtract that again. So 6 minus 5 will give me 1. So I want the first item, first smallest item or the smallest item in the subtree rooted at 93.
Okay.
Okay, I'm not yet done. How do I get to 90 now? Well, I figured out the rank of 93 in that subtree. What is it? 2, right? Why?
What's it called?
How big is the left subtree?
It's 1.
Left subtree is 1, so therefore the root must be the second smallest item. So therefore, since 90 is smaller than 93, its rank must be smaller than 2. Right? So I follow the left child. And this time I don't have to subtract because I'm following the left subtree, not the right subtree. So therefore, I have to simply find the first or the smallest item in the subtree rooted at 90. Since 90 has no children, that is it. That's the answer. And I return it. Did you get that? So remember, I didn't visit any other node. I just started from 61, went to 85, then to 93, and then to 90. This is exactly the path I would follow if I were to search for 90. So therefore, the amount of work I did was the same as the work I would do for search. So therefore, that's a log-in time operation. So what we've figured out is that if I store the size information at every node in the tree, I can solve both rank and select operations in log-in time. Is that clear?
Yes.
So let's get back to the code here that we had. Yeah. This is the rank operation, and this is the select operation. Oops. And as you can see, both are very, very simple pieces of code. In each case, you figure out the rank of the root, you compare your item with the root. If it goes to the left, you have to do something. If it goes to the right, you do something else. Very, very simple. Okay. And in both cases, the time complexity is big O of log n. And so what we have achieved now is something quite spectacular. We've done search, insert, and delete in log n time. And we have now added 2 new operations, rank and select, also executing in log n time. And soon you're going to see some wonderful problems related to rank and select, where your job is to count and figure out where you are in the sorted order, and do all of this efficiently as you insert and delete things. Okay, and we'll see more of that next week, and hopefully you'll become more and more comfortable with this stuff. Any questions?
No, thank you, Professor. This was a very interesting topic actually for me.
Yeah. This is fascinating stuff. The challenge, by the way, for you guys is to turn this into code that works. And if you don't do it this week, this will get lost.
Oh no, okay.
Okay, so you guys need to, and it doesn't matter. I'm not asking you to write the code. Just find some code and get it to work. Okay. And I will send you some information if you want for where to find this code. I've already told you how to find search, insert, and delete for red black trees. Make sure that works. I know not all of you got it to work last Saturday. I need you to get it to work for sure for this Saturday, and also see how you can do rank and select. Okay, you will have at least one problem with rank and select. Is that cool? By the way, it turns out it's not just rank and select. You can do more interesting things with this. So let's see what else we can do. Remember, we are storing this extra information called size at every node in the tree. And what is that? Size is the size of that entire subtree. Size simply means how many nodes are there in that subtree, right? We know that the size of a leaf node is 0 because those are the strange black things, right? If you go above, it's actually quite easy. You can figure out the size of any node in the tree by simply adding up the sizes of the left subtree and the right subtree and adding one more for itself. So you can figure this out fairly quickly. And that's what makes it useful. On the other hand, if you were doing rank, then the rank of the left child and the rank of the right child has nothing to do with the rank of the root. Okay, if you go back to that example, the rank of the left child was actually 3. The rank of the root was 5. The rank of the right child was, I don't even remember now, 9 or something like that. So the rank of the children have nothing to do with the rank of the root. Whereas here, you can simply figure out the rank very easily. Why is that important? It's important because in a red-black tree, you're constantly doing rotations. Remember those rotations we talked about? As you do rotations, it turns out I can easily figure out the size. They can quickly be recomputed and kept to be correct all the time. Not only that, if I'm doing an insert, I always insert at the leaf node. Remember how we did inserts. We do a search, and wherever we fail, that's where we insert. So if we follow a path down to the leaf and insert a node, you just have to follow that same path backwards and increase the size by 1 for every node along that path. So insert is very, very easy. You can just update the size very efficiently with very little extra work. Same thing with delete. If you delete a node, it turns out that there is some efficient work that you can do to recalculate the sizes. So it's not only important to store the right kind of information, but it's also important to be able to update that information as you do these various operations. In particular, as you do insert and delete, you should be able to update those values. That's why size is fabulous. If you kept rank, there is no way to keep track of it. Just because you inserted something here, it could change the rank of everything on the other side of the tree. And that's just crazy. We can't deal with that. Okay. Whereas size, when I change something here, it only changes the size of this subtree. It does not affect anything else. And that's very, very important. That's why this augmentation is useful and works. So this, you can ignore this for now. Now there are a bunch of things that you can store and maintain it efficiently. There are a bunch of things that you cannot. So for instance, forget the first bullet. The second bullet says height of the tree. What is height? Height is the distance from the farthest leaf. Okay. And it turns out that height is an extra piece of information you can store and maintain it quite efficiently, no problem. On the other hand, if I can define something called the depth of a node. Depth of a node is the distance from the root. Height of the node is the distance from the farthest leaf. Now, depth of a node is not easy to maintain. Why? Anyone know this?
Because we might be rotating and it might change the location of the node.
That's right. So what's important to understand is that when you do a rotation, the height of each of the subtrees does not change. But when you do a rotation up at the top of the tree, it could change the depth of everything below it. And that's no good. You can't go and change the depth of every node in the tree. That just you'll never be able to maintain it. Height is great because even though I changed something here at the top of the tree, it did not change the heights of any of the other nodes in the underneath here in the subtrees. That's why it works. I can also keep track of sum. I can sum up all the values in the subtree and store it, no problem, because even though I rotate it, I'll be able to maintain this. I can also maintain next and previous and so on. So the rest are not so useful. So I can do sum, I can do product, I can do a bunch of other useful things and store it in any node in the tree. So I'm going to stop here. I think the time's up. Do you have questions that I can answer? So what you'll see is that there may be some problems where you have to either count or sum up and store information in each node in the tree. Okay, those are the kinds of problems you're likely to see over the weekend. I'm not going to break your surprise. You can show up on Saturday and have fun. So this week we'll have a regular competition. Next week, remember, we are going to do the ICPC's whatever they're doing for the practice run, and then the following week would be your real competition. So I'm going to keep reminding you about the competition. So work on this, okay?
Thank you, Professor.
Thank you, Professor.
Bye, guys.
Thank
Bye,
you,
Samara.
Professor.
Yeah.
Thank you.
Take care.